A vector space gives us addition and scalar multiplication. Useful. Yes. Geometrically charming. Not yet. Linear algebra already knows how to combine vectors. But it still does not know which vectors are long, short, or at right angles. An inner product is the extra gadget that turns algebra into geometry. Because apparently vectors needed accessories. An inner product takes two vectors and returns a scalar. That scalar measures how much the two vectors point in the same direction. The field F is either the real numbers or the complex numbers. Naturally, the complex case refuses to behave exactly like the real one. Over the real numbers, the inner product is symmetric, linear in each input, and positive on every non-zero vector. Over the complex numbers, symmetry becomes conjugate symmetry. We use Axler's convention, linear in the first slot, conjugate linear in the second. The conjugate is not decorative seasoning. Without it, complex length would wander into the complex plane, which is not a personality trait we need. Now for examples. First, the usual real coordinate space, where the inner product is the dot product everyone met before and then immediately underestimated. For Rn, the formula is the sum of matching coordinates multiplied together. For Cn, the standard inner product conjugates the second vector. Again, this is not optional decoration. It is structural plumbing. For real continuous functions on an interval, multiply the functions and integrate. The inner product is no longer a finite sum, but the idea is the same. For complex valued functions, conjugate the second function inside the integral. The complex numbers are dramatic, but at least consistent. Once an inner product is available, three geometric words finally become legal: length, orthogonal, and angle. Think of two non-zero vectors u and v. The picture is familiar, but the formulas now come from the inner product, not from staring at arrows with optimism. The length of v is the square root of the inner product of v with itself. We are not using the official name for this length yet. Patience. Apparently, vectors u and v are orthogonal when their inner product is zero. This generalizes perpendicular arrows, without requiring every vector to live in a drawable universe. In a real inner product space, define the angle by arcos of the normalized inner product. This automatically keeps theta between 0 and pi. In complex spaces, the inner product may be complex, so the ordinary geometric angle uses the real part. Complex phase is useful, but it does enjoy making definitions less cute. So the inner product is not a random bracket. It is the mechanism that lets a vector space talk about geometry. Next time, this geometry will start proving theorems. Cauchy-Schwarz, the triangle inequality, and all the usual responsible behavior.